Okay, what we should have seen from the lab that you did in class was after you touch the pie pan to the Van de Graaff, you notice that the Van de Graaff caused the pie pan to have a negative net charge. And if you look closely, I drew in the extra electrons. I'm just highlighting those extra electrons for you that must have been transferred from the Van de Graaff to the actual pie tin. That being said, the pop can started off as neutral. So with the neutral pop can, you then brought it together to the pie pan that was negatively charged. And if you look at your data table as to what happened after, you see that both the pie pan and the pop can attracted the top tape and both repelled the bottom tape. This is enough evidence to show us that the pop can and the pie pan must both have a negative net charge. So after, you can understand that this was negative and this was negative. So what had to have happened during this process of touching the two together? You can't just transfer all of these electrons over to the pop can, because then the pop can would be negative and the pie tin or the pie pan would be left neutral or positive. If you take just a few though, and since I have 6 extra electrons, I'm going to take 3 of them. All 3 of them are going to transfer over to that pop can and be placed as excess electrons on there. So now if I come down, I draw those 3 extra electrons on the pop can, and then I'm only left with 1, 2, 3 excess electrons on the pie pan. So that is that first part of the lab, the first page, where we had the negatively charged pie pan touching a neutral pop can. Electrons must have been transferred from the pie pan to the pop can, leaving both with a net negative charge. We will define this on the back, but this is something, again, that we will call conduction. So this process of touching and having a charge transferred is called conduction. We already talked about induction and polarization before, but this is a new method for us. If we go on to scenario 2 shows us this pie pan that was actually charged through using the fur and the pink foam. And if we look at that from our lab, you can remember or go back to it or at least test it. After rubbing the pink foam with the fur, we remember from our last lab that the pink foam had a negative charge and that the aluminum pie pan now carries a positive charge to start with. They ask you to then test that, and we see that there is a positive net charge on the pie pan. And again, the pop can started off as neutral. You touched the two together and then you took data to see what the final charges were. On the back side, this is the back side, but I'm just going to kind of carry it down for you. By looking at your data, after you touched the two together, both the pie pan and the pop can repelled the top tape, which tells us that both the pie pan and the pop can are positively charged. So this carries still a positive net charge and a positive net charge on the pop can as well. So what must have happened while they were touching to make both things positive? Some people are inclined to say, well, it must have been the protons moving over because that will cause this to be positive and you still have this positive. But we said protons don't move. Those are tightly held in the nucleus of the atoms. And the electrons are the things that are mobile, not the nucleus or the nuclei themselves. So if this happens, we're going to show that positive net charge by this one is lacking 4 electrons. And our neutral pop can is already done for us. So what's the other way you can make something positive? We have to only move electrons. If I take electrons away from my pop can, that will leave this positive. If I bring them to the pie pan, it will also leave it as a positive net charge. But the thing we have to be careful about is we can't add more than, through my example, 3. If I added 4 electrons, or took 4 electrons from here, yes, this would be positive, but now this one would be neutral. If I put 6 all on here, then this one would have a net negative charge. So through this example, I'm just going to take 2 electrons. So 1 electron here is going to go through and into the pie pan, and 1 electron here is going to go through and into the pie pan. That leaves us with an electron transferred over here, 2 on this part, and we are only left with now 4 electrons on the pop can. This does, if we look at our net charge for each one, 1, 2, 3, 4, 5, 6 protons, 1, 2, 3, 4 electrons, leaves us with a net positive charge. And on this one, 1, 2, 3, 4, 5 protons and 1, 2, 3 electrons also leaves us with a net positive charge. So that is kind of the simple explanation as how these objects got charged the way they did. And again, this second scenario is called conduction as well. So looking at that on the back side still, what is conduction? Conduction is really defined in a few different ways. We are more so talking about conductive charging. Conduction can also be talking about some other things, but conductive charging is what we're referring to. So the definition for that is when an originally neutral object becomes charged after touching a charged object. Now notice the most important part with this, or the most distinguishing part from our other induction and polarization, is that there is touching. I like to look at it thinking conduction has contact. So there is contact made between the two items, the neutral and the charged object. This also just happens to work best for conductors. That being said, those electrons can freely move, so the conductor is a better way for those electrons to go to one side or the other, just kind of share between the two objects as they touch. Insulators, it doesn't work as best for, and we're going to really say that conductors are the best thing to do this for. The procedure for this is pretty simple as well. Touch a charged object to a neutral object. In both scenarios, both the first one where we had the negatively charged pie pan and the second one where we had the positively charged pie pan, we saw a charge transfer for both of them. And both of them ended up leaving the pop can that was originally neutral with a net charge. Take a second and think to yourself, this is a very similar table to what we did on our other note sheet. So we're going to compare it with our past knowledge and again summarize some of these concepts in here. So hit pause, take a second, and fill out that bottom chart as best you can, and then hit play again when you're ready to go over it. Okay, looking back, Polarization does not have contact made between a charged object and a neutral object. Charges are not transferred between that charged object and the neutral object, and there is no net charge or no change in net charge, so does not apply for that last category. Induction, we said the first step was to polarize it, so no, you are not having contact between the charged object and the neutral object. No, charges were not transferred between the charged object and the neutral object. If you wanted to clarify, because you did know that some charges were transferred, the ground is what touches the neutral object. And for the fact that there are charges transferring, the charges transfer between the ground and the neutral object. And that did, yes, cause a change in net charge. If we remember back, if I had my originally charged object as positive, my newly charged object was negative, and vice versa. So those are the opposite charges that you will end up with. For conduction, this is what we just went over from this lab and kind of defined above. There is contact made between the charged object and the neutral object. And if you're referring back, this is where that happened. We had our pie pan that was originally charged, our neutral object, and they touched. So that is the part where, yes, there is contact made between them. Did charges transfer? Yes. We decided that to end up with a net negative charge on both of those, electrons had to have moved from the pie pan to the pop can. So charges did transfer between them. Did it change cause a change in net charge? And that's speaking for the originally neutral object. And the answer was yes. Thinking back, now the pop can carried a negative charge. The last question on there is asking, how does this new charge compare to our originally charged object? And if we can see, they are the same. My originally charged pie pan was negative. My pop can ended up negative. For even the second scenario, my originally charged pie pan was positive, and my pop can ended up being charged positive. So positive charges, or positively charged object, when conduction happens, will cause your originally neutral object to be positive. Negative will cause negative, and vice versa. So looking back, that means that the same charge is what you result in from your originally charged object. A couple other things to go over. We did talk about grounding a little bit more today. The grounding happens, so grounding is not really necessarily that you're talking about the charged object and the neutral object, but it can be considered for a couple different ways. A ground can touch either a neutral, which meaning for our case is polarized, object, or a charged object. In both of these cases, yes, charges transfer. And then the second part where it says, does it cause a change in net charge, and what would that net charge be? Again, this is not as easy to fill out for both of those categories, but if you say the ground gains or loses electrons, that's true, but we say it's not enough to matter. So it's not enough to say that there's a change in net charge of the ground. And if you ground a polarized object, the object will become charged. That's kind of our induction example. If you ground a charged object, the object will become neutral. So those are a few different scenarios where we see grounding used. All right, that seems like the summary of our lab and our 3 different methods that we saw, or 2 different methods where we saw charging. Our one method that we saw caused an attraction between polarized objects and charged objects, and the grounding that way how we contribute to those in those procedures. All right, enjoy.